This video provides an overview of the User Datagram Protocol, or UDP. We'll explore how it facilitates connectionless communication and examine its various use cases. So, what exactly is User Datagram Protocol? UDP stands for User Datagram Protocol. It is a connectionless transport protocol. This means that unlike TCP, UDP does not establish a connection before sending data. It's an integral part of the Internet Protocol suite and is known for its minimal overhead, as it doesn't involve any handshaking processes. Let's examine the structure of a UDP header. The UDP header comprises of 4 fields: source port, destination port, length, and checksum. The source port, which is 16 bits, identifies the port number of the sending application. The destination port, also 16 bits, specifies the port number of the receiving application. The length field, again 16 bits, indicates the total length of the UDP datagram, including both header and data. The checksum field, 16 bits as well, is used for error detection. It allows to check the integrity of the data. The UDP header is only 8 bytes in size, making it extremely lightweight compared to TCP's 20-byte header. This minimal overhead contributes to UDP's speed and efficiency. Now let's explore the key characteristics of UDP. First, it is connectionless, meaning there's no handshaking process involved. Second, it offers low latency and overhead, making it ideal for applications where speed is crucial. Third, there's no guarantee of delivery, so packets may be lost along the way. Also, there's no packet ordering, meaning packets may arrive in a different order than they were sent. And lastly, it provides basic error checking only, without the advanced reliability features of TCP. Let's compare UDP with TCP. In terms of connection, UDP is connectionless, while TCP is connection-oriented. For reliability, UDP provides no guarantees, whereas TCP ensures guaranteed delivery. Regarding ordering, UDP does not guarantee packet ordering, while TCP ensures ordered packets. In terms of speed, UDP is faster, while TCP is slower due to its reliability mechanisms. The header size of UDP is only 8 bytes, while TCP has a larger header size of 20 bytes. And lastly, UDP has no flow control mechanisms, whereas TCP incorporates flow control to manage data transmission. Let's explore some common use cases for UDP. Online gaming benefits from UDP's speed, where occasional packet loss is acceptable for maintaining low latency. Video streaming utilizes UDP for real-time delivery, where minor frame loss is preferable to buffering. Voice over Internet Protocol, or VoIP applications rely on UDP for continuous audio flow, where small audio drops are better than delays. Domain name system, or DNS lookups use UDP for simple queries where speed is essential. Internet of Things, or IoT telemetry utilizes UDP for sensor data, where frequent updates are more valuable than guaranteed delivery. Lastly, time-sensitive applications benefit from UDP's timeliness of data, crucial for real-time analytics and monitoring systems. Let's explore a simple UDP server implemented in Python. First, we import the socket library. Then we create a UDP socket using socket.socket, specifying address family inet and socket datagram. We bind the socket to a specific address and port using sock.bind. In a loop, we receive data from incoming clients using sock.recfrom, which returns both the data and the client's address. Finally, we send a response back to the client using sock.sento, specifying the client's address. Key components here include the use of socket datagram to specify the UDP socket type. Notice that no listen or accept calls are needed in UDP programming. Also, recfrom returns both the data and the sender's address. And lastly, sento requires the destination address with each call, as no connection state is maintained. Unlike TCP, there's no connection establishment in UDP. Each packet is independent, and we must include the destination address with every send. And importantly, there's no stream abstraction, so message boundaries are preserved. It's worth noting that UDP applications must implement their own reliability, ordering, and congestion control mechanisms if needed. Here are some common protocols that are based on UDP. DNS, or Domain Name System, uses port 53 to translate domain names to IP addresses. DHCP, or Dynamic Host Configuration Protocol, uses ports 67 and 68 to assign IP addresses to devices. SNMP, or Simple Network Management Protocol, uses port 161 to monitor network devices. RTP, or Real-Time Transport Protocol, uses dynamic ports to carry audio or video streams. NTP, or Network Time Protocol, uses port 123 to synchronize clocks between systems. And QUIC, developed by Google, uses port 443 and is built on UDP with added reliability features. UDP's simplicity and low overhead make it the foundation for many specialized protocols that require speed and efficiency, even if they can tolerate some packet loss. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.